Last time when we talked about optimization, we talked about what you might call local optimization, meaning find critical points, check to see whether they give you a local max or a local min with what I call the first or second derivative test. Today, the focus is more on global optimization, finding global or absolute highest and lowest points on graphs, global maxes and mins. But you should realize that in general, to be able to do such a thing for a nice continuous function, you might have to focus on a closed and bounded interval and not the entire real number line. For example, let's take a cubic. F of x equals x cubed minus 3x squared plus 20. We're trying to find the global max and global min values of this function over a certain interval. And the example in the book goes from -1 to 3. Let me pick something different. How about -2 to 4? So there is my closed and bounded interval here. Closed and bounded interval, sometimes called a compact set of the real line. In interval notation, which you should be comfortable with, interval notation, we'd use square brackets, not parentheses. This right here means the closed interval from -2 to 4, all the numbers between -2 and 4, including -2 and 4 themselves. So if you were drawing the interval, you'd want to have filled in dots at -2 and 4. That's a closed and bounded or compact interval. There, question?
Is there a way to do it with like union?
Question was, can you make a bigger interval that's also closed and bounded, meaning union this with other disjoint intervals like from 8 to 16 or something? And the answer is yes, you can. This function is a nice function. It's a cubic. You're never dividing by 0. It's nice and continuous everywhere. It's nice and differentiable everywhere. The fact that it's continuous, f is continuous on the interval from -2 to 4, implies by something called the extreme value theorem. Extreme value theorem, not the mean value theorem, the extreme value theorem, that f will have a global or absolute max and a global or absolute min on the interval. The extreme value theorem is what guarantees it. Now, I'm not going to state the extreme value theorem, but basically it's saying what I just said. If you've got a nice continuous function defined in a closed interval and continuous on that entire interval, you're guaranteed to have a high point and a low point. Before I try to find those high and low points, let me remark that the fact that the interval is closed and bounded is essential. This is a side example, but it's something you should know about. Like if f of x equals x, and your interval is the interval from, say, 0 to 1, open interval, for extra emphasis, I'm making open circles at the origin and at the point 1, 1 to indicate that those are not points on the graph. That function on this open interval has no high point and no low point. There is no highest point to this graph and no lowest point. You might wonder, well, isn't 1 the highest point? The answer is no, it never gets to 1. It gets really, really close, arbitrarily close. In fact, you can get to 0.9, you can get to 0.99, you can get to 0.999. 0.99999, 0.9999999. In fact, you can get to point any finite number of nines, but you don't get to 1. That's in spite of the fact that 0.9 repeating does in fact equal 1, but I never said we're getting to 0.9 repeating. You want to argue with me about that? We can talk after class. It does. 0.9 repeating does equal 1 for sure, guaranteed. Okay, and I can explain why after class if you're interested. Does it have a low point? Is it 0? No, it never gets to 0. It gets to 0.1 and 0.01 and 0.001 and 0.0001, but no, it never gets to 0. So the interval does have to be closed and bounded to be guaranteed to have a max or min. If you consider f of x to be x over the entire real number line, that also has no high point, no low point. It keeps going up and down forever and ever. So it's got no high point and no low point. Or could you say the high point is infinity? Not in this class, you can't. So don't. How do you find the high and low points? The algorithm is this. This is the algorithm or method to find the global max and global min. First step, find the derivative of f, set it equal to 0 to solve for critical points. Oh, well, careful. Critical points can also occur where f prime is undefined. The function is not differentiable. So let me just say, find the critical points of f. Usually those are found by taking the derivative, setting it equal to 0, solving for x, but not always. Because sometimes you got to look for places where the derivative is undefined as well. Find the critical points of f. Plug the critical points of f and the endpoints of the closed and bounded interval, which in general I'll write a to b, into f. Step 3, identify the highest, greatest, and lowest, also called the least, values from step 2 for those are the global max and min values. You're done. So let's apply it now with our cubic example. Again, f of x equals x cubed minus 3x squared plus 20. Find the critical points first, take the derivative. Here's what it is. Set it equal to 0 and solve for x. You're always hoping you can factor if possible, and we can here. And we see there's 2 critical points at 0 and 6. Which reminds me, I need a caveat in my algorithm. In step 2, I should have also said plug the critical points of f that are in the interval. Yes, you could find all the critical points of f if you want, but you only want to work with the ones that are in the interval that you're talking about. Question? Yes, thank you. So your critical points are 0 and 2. Those are both in the interval that I picked. If they had been 0 and 6, the 6 would not have been in the interval. What interval did I pick? Again, it was over the interval from -2 to 4. 0 and 2 are both in that interval. 6 is not, but 6 is not a critical point. I made a mistake. Where am I here? I just finished step 1. Now I'm on to step 2. Plug the critical points of F and the endpoints of the interval into F. You can make a little table if you like. The endpoints are -2 and 4. The critical points are 0 and 2. How about that? Those are all equally spaced. I did not plan that out. That's just a coincidence. What's f of -2? It's -8 minus 12 plus 20, which is 0, amazingly. What's f of 0? It's 20. What's f of 2? It's 8 minus 12 plus 20, and that is 16. What's f of 4? 4 cubed is 64. 4 squared, 16 times 3 is 48. 64 minus 48 is 16 plus 20 is 36. That look good to people? What's the highest value? 36. There's the global max value. Global max value. Where's the lowest? That's 0. That's the global min value. Can we confirm this graphically? Yes, question?
How do we know that they're globally the maximum? Like, what if there's a higher point outside of the range you picked?
We're only focused on this interval. We're ignoring everything else. That's why.
Okay.
Between -2 and 4, well, f of -2 is 0. F of 0 is up to 20. F of 2 is down to 16. F of 4 is back up to 36. The graph looks like this. On this interval, both the global maximum and the global extrema occur at the endpoints in this example. There's your global min, there's your global max. When I put the word value in there, I mean output. I mean second coordinate, y value. 0 is the global min value. It occurs at x equals -2. 36 is the global max value. It occurs at x equals 4. There are local max and local mins here as well. We don't want to ignore those. It looks like probably a local max occurs at 0, and a local max value is 20, and a local min value of 16 occurs at 2. How could we confirm that those are local extreme points? That's the previous section. First and second derivative tests. If I were to use the first derivative test here, think with me here. Think very clearly about this. Remember, what does the first derivative test say? It says at a critical point, like at x equals 0, if the derivative changes sign from positive to negative, meaning the original graph changes from increasing to decreasing, there'll be a local max there. Does this derivative change from positive to negative as x increases through 0? Drawing a number line is helpful. Imagining plugging numbers in is also helpful. If you plug a number less than 0 into here, like -1, you get a negative times a negative, positive, f prime's positive. Oh yeah, I can see it in the picture. Plug in a number between 0 and 2, like 1, positive times negative is negative. Plug in a number bigger than 2, like 3, you get a positive times a positive. So f prime changes from positive to negative as x increases through 0. That's why there's a local max at 0. It changes from negative to positive as you pass through 2. That's why there's a local min at 2. That would be how to use the first derivative test to verify local max at 0, local min at 2. Drawing pictures like this is enough work for me, but you should also state what your final answer is. I mean, you should see the factored form, and then you draw a picture like this, label where the derivative is positive and negative, and then state your conclusion that that means there's a local max at x equals 0 and a local min at x equals 2. The local max value is 20, the local min value is 16. Okay, so I did both kinds of problems here. I did a global extreme problem first, thinking about the endpoints as well, and the global extrema were at the endpoints. And I did a local extreme problem at the critical points here, and found this was a local max and this was a local min, just like you can see with the picture. And yes, global does imply local. There's not only a global min at -2, that you could also call that a local min. It's not a critical point, but it is the lowest point on the graph near x equals -2. And this global max at x equals 4, you could also call a local max. Again, it's not a critical point. The derivative is not 0 there, but it is the high point, not only globally over this interval, but also locally. It's the high point if you plug in values of x close to 4. Let's next consider the example f of x equals x times e to the -x squared over 2. And I'll pick a different interval than the book does. Once again, you should feel comfortable either with inequality notation or interval notation. I'm after global extrema in section 4.2. I need the algorithm. I need to first find the critical points of this function. Second, plug those critical points into the function as well as the endpoints. Third, identify the greatest and least of the numbers that I get out for outputs. And then fourth, say what the answer is. Find the critical points first. It's a product, so we need the product rule. Left x, d right. I need the chain rule to differentiate that. It gives me an extra factor of -x. Right? Differentiate -x squared over 2. Bring the 2 down, it cancels with the 2 in the bottom, giving you a -x. That's the derivative of -x squared over 2. That's left d right plus right. D left is just a 1. I want to set this equal to 0 and solve for x to find the critical points. It's good to factor out anything that can be factored out. There's a common factor of e to the -x squared over 2. What's left over is a -x squared and a +1. Set this equal to 0 and solve for x. E to a power is never ever 0. Some engineers say e to the -infinity is 0. But remember, infinity is not a number for us. So for us, e to a power is never ever 0. Yeah, if you had to pick what e to the -infinity should be, you would say 0. But infinity is not a number. So this being 0 means you can ignore the e part and say this is 0. But that means x squared is 1. Which means x itself is plus or minus 1. There are 2 critical points where the derivative is 0. If we were after identifying these as local extreme points, we'd use either the first or second derivative test. I forgot to remind you what the second derivative test said on that other problem. But we're after global extreme values here, so It's actually, you might say, a little conceptually easier. You can just focus on the endpoints and the critical points and plugging those into the function. Make a table again. -3, -1, 1, 3. These are equally spaced as well. That doesn't always happen. Doesn't usually happen, in fact. F of -3. Go back up to the formula for F. You'll get -3 e to the negative of -3 squared over 2. Right? You replace the x with -3. This negative sign in front of the x squared there, order of operations would get done after you square x. So when I plug -3 in there, I square it first before I multiply by -1. -3 squared is +9. But you do have a negative sign there. So in the end, you do get -9/2. F of -1 is -1 e to the negative of -1 squared over 2. Giving you this. F of +1 is +1 times e to the -1 squared over 2. Positive e to the -1/2. Oh, this is an odd function. F of 3 is +3 e to the -3 squared over 2. +3 e to the -9/2. Careful, these e's are to negative powers. So these e's are small numbers. And in fact, the smallest of them is e to the -9/2 is smaller than e to the -1/2. So even though it sort of looks like this one might be the biggest number and this one might be the smallest, that's actually wrong. Those are negative powers of e. It probably would be best to approximate, well, these two numbers with my calculator and then negate them for these two numbers. E to the -1/2 is about 0.607. Three times e to the -9/2, also -4.5, is closer to 0. Very close to 0, in fact. 0.033. These numbers are just the negatives of those. So this is -0.607, and this is -0.033. So the largest number here is this one. There's your global max value. And your smallest number is this one. There's your global min value. This time, those are occurring at the critical points, plus or minus 1, not the endpoints. The graph in this situation happens to look about like this. And say -3 is right there and +3 is right here. 1 is going to be there and -1 is going to be here. Your global max value corresponds to this point right there. Your global min value corresponds to this point right there. It's not a global max or min at the endpoints for this example, as opposed to the other example. Could a global min occur at an endpoint and a global max at a critical point in the interior? Yes, that could happen. Could I make up such an example? I won't make up a formula, but I'll draw a picture. What did I say? Could a global min occur at the left endpoint, but the global max not at the right endpoint? Sure, if you had a graph like this, that would be a graph where the global min occurs at the left endpoint, but the global max occurs at the critical point. And that's not an endpoint. It's in the interior of the interval. That can happen. Likewise, you could have a global min at the right endpoint and a global max at an interior point as well. All different kinds of combinations can happen. If we were after local maxes and mins in this problem, being a global min there means it would also be a local min. Being a global max there would also mean it's a global max, a local max. This one is not a global min or a global max, but it is a local max. It's higher than nearby points. This one's not global max or min, but it is a local min. It's not global, but it is local. If we wanted to confirm that these points were local min, local max, we could use the first derivative test like we did before, or we could use the second derivative test. We could find f double prime of x, whatever it turned out to equal. I won't bother doing it. If we plug in 1 into f double prime, what will we get? I don't know what exact number we'll get, but I can say it'll be negative. You can see the graph's concave down near 1. And that being negative by the second derivative test would be enough to say you've got a local max at 1. Likewise, f double prime of -1 would be positive. This graph's concave up near -1. And that would be enough to say you've got a minimum min. As I said the other day, you can use either the first derivative test or the second derivative test. You don't need to use both. One or the other is usually fine, though sometimes the directions say use the first derivative test. Sometimes they say use the second derivative test. I will tell you, however, and you should know this for the next exam, that the first derivative test is technically more powerful than the second derivative test. What does that mean? It means there are some examples, they're typically kind of a little strange, where the first derivative test tells you what happens, but the second derivative test tells you nothing. Simplest such example is f of x equals x to the 4th. This is a function whose derivative is 4x cubed. If I set that equal to 0 and solve for x, I get a critical point at 0. 0 is a critical point. And that derivative there, that 4x cubed, is negative when x is negative. Negative. Negative when x is negative, and positive when x is positive. And that means the graph of f itself is decreasing when x is negative and increasing when x is positive. There's got to be a local min at 0. In fact, the graph looks like kind of like a parabola, though it's flatter than a parabola near the origin. It kind of looks like this. This is kind of what the graph of f of x equals x to the 4th looks like. It's not technically a parabola. It's flatter than a parabola is near the origin. And you can see there's not only a local min at x equals 0, but it's even a global min. However, if you try to use the second derivative test here, it will tell you nothing, because the second derivative is 12x squared, and if you plug 0 into that, you do not get a positive or a negative number. You get 0, which is not positive, and it's also not negative. It's 0. So technically, the second derivative test is telling you nothing. Now, you might look at this graph and say, hey, wait a minute. Isn't this concave up everywhere? And in a sense, yeah, it is. But at the same time, the second derivative at 0 is 0. And so, yes, the second derivative test tells you nothing. In a sense, the concavity at the origin is 0, because the graph is so flat near the origin. If you zoom in near the origin, it'll be indistinguishable from the x-axis. And you don't even have to zoom in very far. That's how flat it is. That's an example that you should know about for the next exam. It might show up on a true-false or multiple choice question. I have put it on old exams. So the first derivative test confirms it's a min, but the second derivative test tells us nothing in this example. But mostly you can use either one. sometimes the questions are phrased a little strangely. Sometimes the directions say, find the best possible bounds for the function, instead of saying, find the global max and min values. Well, guess what? It's just another way of rephrasing the same question. The best possible upper bound of a function is its global max value. The best possible lower bound for a function is its global min value. They really are the same thing. Why don't we try 25 here? Function is x plus sine of x over the interval from 0 to 2 pi. Find the best possible bounds for that function. On that interval, f of x is x plus sine of x over the interval from 0 to 2 pi. I'm using interval notation now. To find the best possible bounds is the same thing as finding the global max and min values. So you use the same algorithm. You find the critical points. You test the value of the function at the endpoints and the critical points. The biggest number is the global max value, also called the best upper bound. The lowest number is the global min value, also called the best lower bound. The derivative here is 1 plus cos x. If I set that equal to 0 and solve for x, I get cos x equals -1. If you use the inverse cosine function here, that's fine, but realize that's only giving you one possible answer. There are infinitely many values of x where the cosine of x equals -1. Remember our old friend, the bug? Unit circle. The bug goes on the point 1, 0. The cosine is the first coordinate. The sine is the second. Cosine is -1 over at the leftmost point of the circle, when the angle is pi radians, or 3 pi radians, or 5 pi radians, or 7 pi radians, 9 pi, 11 pi, etc. You could also go the other direction, -pi, -3 pi, -5 pi, -7 pi. Of those, which one is in the interval from 0 to 2 pi? Just pi. If I apply the inverse cosine function to this, would I get that answer? You do happen to for this example, but if I change the interval, you would not. Possible solutions are a bunch of inverse cosine. It's cosine of inverse cosine of 1 plus integer multiples of pi. Typically written like this, 2n pi, where n is 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. These are infinitely many numbers that all make this equation true. So there are infinitely many critical points to the original function. But only one of them is in the interval from 0 to 2 pi, and that's just inverse cosine of 1, which is -pi. Or not negative pi, positive pi, sorry. Question? Oh, it's because I made a mistake. It's a -1 then. Thank you. Oh, but this should be a plus pi. Sorry. If you want to confirm it, make sure your calculator is in radian mode, as mine is. Inverse cosine of -1 should be a pi. Positive pi, yes it is. Why? It's because of how inverse cosine is defined. Inverse cosine of a number between -1 and 1 is thought of as being an angle between 0 and pi, whose cosine is -1. Well, pi, 180 degrees in that range in the first or second quadrant is the unique angle whose cosine is -1. second coordinate of that point over there, or first coordinate is -1. So in the interval from 0 to 2 pi, it means x is just pi. N is 0. So there's your one critical point. To finish the problem, check the value of the function at the endpoints and the critical point. 0, pi, and 2 pi, and they're evenly spaced again. Don't be misled into thinking that always happens. F of x is x plus sine x, so I get 0 plus sine 0 here is 0. When I plug in pi, I get pi plus sine pi is pi plus 0 is pi. When I plug in 2 pi, I get 2 pi plus sine 2 pi is 2 pi plus 0 is 2 pi. That's kind of strange, but true. There's your global min value. That's the same as the best lower bound. They're just different names for the same thing. Global min value is the same thing as the best lower bound. Global max value 2 pi is also your best upper bound. What does the graph look like here, and why are these called best lower and upper bounds? The graph of f of x equals x plus sine x between 0 and 2 pi turns out to look like this. F of 0 is 0. F of pi is pi. The second coordinate there is pi. F of 2 pi is 2 pi. It's only at pi that you have a horizontal tangent, a critical point. And because it's also an inflection point, as you can see here, it's neither a local max nor a local min. This derivative is never negative, because cosine of x never goes below -1. On either side of the critical point, f prime is positive. So even though there's a critical point at pi, it's not a local max or a local min. For this interval, it's also not a global max or global min. The global max is min is at 0, the global max is at 2 pi. And why are those called best upper and lower bounds? Because the global max value, 2 pi, is typically thought of as representing a horizontal line that the graph doesn't get above. So that horizontal line at y equals 2 pi is an upper bound for this function. It's higher than the function, and it's the best upper bound. It's the lowest possible horizontal line that's always above the graph. That's the best upper bound. The best lower bound is at 0. That's the highest possible line that's below the graph all the time. And we could even write inequalities. We could say 0 is less than f of x is less than or equal to 2 pi for all x in the closed interval from 0 to 2 pi. That's something we can say here. We can write inequalities. This is often a very useful thing, especially in chapter 5, when we get into integrals, definite integrals, as opposed to indefinite. Knowing best upper and lower bounds for functions can help you think about how to approximate integrals as good as you can. So that's where this is most useful, is in approximating definite integrals. Sometimes definite integrals, areas under curves, have to be approximated. You can't find them exactly. We will see that a little bit in chapter 5 before the end of the semester.